Okay, so there is an energy content in food, and you may have noticed that we were talking about calories before. And so this is the amount of energy that's released for 1 gram of that to increase water by 1 degree Celsius. Okay, and that was the definition of a calorie. Now, when we eat food, we don't burn it, but we do oxidize it. It's a very similar process to burning it. Okay, and so when we talk about burning calories, this is actually what we're going to be talking about. It's the amount of energy that's released by that type of food. For example, carbohydrates releases 4 capital C calories per gram of that. Okay? And when we talk about protein, it releases 4 capital C calories per gram. And then when we talk about burning fat, every gram of that is going to release 9 capital C calories per gram. Notice I keep repeating that word, right? Capital C. Okay? Okay. So when we look at calories, the lowercase c is the actual unit. Okay? And so that is the one that is 1 gram of water is being heated 1 degree Celsius. Okay? By that amount of energy. Now, when we see the capital C, that's actually a kilocalorie. That's 1,000 calories. So when you look at the packages, that capital C is the one on the packages of your food that you may have seen. It's 1,000 actual calories. Okay? I know, it's confusing. It's weird. It's really kind of a stupid thing to do. They could have just put the lowercase k in front of it, and it would have been correct. But they did that. Okay? This right here is the kilojoules per gram. This would be the equivalent kilojoules per gram with the equivalent conversion factor. Okay? If you actually look at different countries will list, the United States mostly will list calories per gram. It's capital C calories. The other countries mostly list kilojoules because it's the SI unit. Okay? Interestingly enough, if you actually look at food that's sold internationally with the same packaging, they'll just have both. Right? Okay, everybody's seen that before? Fantastic. Okay, so here's some different nutrients, different foods, and their different compositions. Right, there's carbohydrates, proteins, fats, and their calories. Now, keep in mind that whenever you're talking about calories on a package label, this would be the amount that if you actually burned it. Okay? A human being does not harvest that entire amount. It depends on how efficiently you digest things. Okay? So they typically range in the somewhat like 80 to 90% for most humans, though it can be different depending on the nutrient. An interesting side note to this also is the carbohydrate numbers on here oftentimes are not actually what's in the food or what's being digested in American labels. Anybody know how an American label works? Yeah. So how an American label actually works, except for alcohol. So you guys don't have to worry about that yet. Okay? Hopefully. Is when you look at an American label, if you looked at something like kombucha. Does everybody know kombucha? Okay, it's a fermented drink. Okay, very similar to alcohol, actually fermented. Now, what happens is that whatever they put in to that mixture, that's what they have to list on this label. And so, for example, kombucha looks like it's very high in carbohydrates and is actually not very high in carbohydrates because the fermentation to get that fizziness, it actually uses up most of that sugar. Okay? So it's kind of an interesting dichotomy that what you actually eat is oftentimes pretty divergent from what the label says, but at least it's a standard and people can't cheat it easily. Okay. All right. So carbohydrates also have another interesting complicating factor that when you eat a lot of fiber alongside the carbohydrates, it can actually cause the carbohydrates not to be absorbed as much. So you actually end up getting less carbohydrates, but things with a lot of fiber. But that's another thing that has variability and just complicates the issue, right? Okay, now right here, some of the different types of food and their different mixes. Is anybody surprised by any of these things? Probably not. Did you guys know butter has protein in it? It's not a huge amount. I wouldn't consider it your source of protein, but yeah, it does have a fair amount of protein because it's a milk based usually, right? Okay, and right here's corn. It has probably more protein than you probably imagined. Anybody have any questions about that? Okay. All right, so right here, when we're talking about these nutritional labels, what are they actually? Well, they are thermodynamics, right? Because we have our grams, and then we have the amount of energy coming out of them. So realistically, these are all generated from thermodynamic studies of these compounds, okay? So this right here would be how we use that label if we wanted to transform it. So we see we have 12 grams, this is times 9. That gives us 108 calories from our fats. We have 15 grams of carbs, it's times 4. And so that would give us 60 calories from our carbs. We have 7 grams of protein, this is times 4. This is going to give us 28 calories. Now, an interesting side note to this is that some of these things do get used to like make new cells, make new muscle, make new, etc. Right? But everything in excess gets converted typically to some form of calorie, which then if you have excess of that, gets transformed into two forms actually. Fat is the one you're probably thinking of the most, but glycogen also, which is that buildup of the hard stuff around the liver. You may have noticed like a beer gut. That's a beer gut. Okay. Okay, we add all of these together, and that gives our total calories right here. So let's talk about some low-calorie foods real quick. So most of the calories in like a soft drink comes from the sugar, right? And so what we end up wanting to do oftentimes is to take sweeteners that are not sugar and will undergo very few chemical reactions in the body, so the body struggles to digest them, okay? And that way they don't produce much energy. In fact, some of them end up taking more energy up than they do try to digest them than they actually get. But fats produce the highest amount of energy per gram when they undergo chemical reactions in our body. That's 9 calories per gram. Manufacturers of baked goods have introduced things like fat substitutes, produce low-fat alternatives. Substances like dextrin, cellulose, and gums are carbohydrate-based molecules. They produce less energy when eaten. I will note, however, there is some new science coming in that a lot of these like sweet alternative sweeteners and stuff and low fats fat substitutes also have some long-term effects that are not necessarily great for you. However, that's an entire discussion with your nutritionist whether it be worth that. Like, kind of like, yeah, you may get back damage from getting yanked up by a rope on a helicopter, but if you're drowning, you probably want to get yanked up by the rope by the helicopter, right? Okay. So, it's trade-offs. Now, let's go ahead and talk about kinetics now. So kinetics is not going to be whether it's spontaneous or not. It's not the total amount of energy released. It's going to be how fast things happen. Okay, it's the rate. So when we measure that rate of reaction, we can determine the amount of product form, or we can use the amount of reactant that's used up over a certain period of time. Because again, this is going to be rate, how fast something happens. So for a chemical reaction to occur, the molecules of reactants, they have to collide with each other. They have to have enough energy to do the reaction, and they have to be oriented properly to do the reaction. Okay? You can think of it a bit like when you try to shake someone's hand, right? You have to have the right orientation, and you have to have enough energy for them to actually collide and grasp each other, right? What happens if you come in, you don't have enough energy? Well, you don't actually grasp, right? What happens if you come in, you don't have the right orientation? Well, you're just going to bounce off each other, right? And so these are the considerations whenever we have a reaction going on. Now, any factor that affects the rate of collision or the energy available to the reaction is going to affect that rate of the reaction. So right here we have some different kind of examples of or theoretical examples for our minds to follow of these reactions. So we have two things that when they collide produces a third thing, right? So when we have more energy, what typically happens to reactions? So cooking is a reaction, right? So when we provide more energy, we cook at a higher heat, what happens to that reaction? Cooks faster, doesn't it? Okay. And so the reaction goes faster when you provide more energy. When you start off reactions and every single particle is reactants, well, you have a lot more chance of getting collisions, don't you? Between the two reactants. What happens as you go on and you get less and less and less reactants? Well, you're going to have less and less chance to collide and produce that reaction R2. Okay? So that's another source where things start to slow down. Okay, so temperature is usually the thing we can control the most and the thing we usually consider the most when we're talking about reactions. Okay? And this is the one that's probably going to click best in your minds because you all kind of know this already. Because how do you speed up something cooking? Higher temperature, right? And so what's happening when you increase the temperature of something? Well, you're increasing the kinetic energy, that motion of those particles, right? And so they're going to collide more often because they're bouncing around faster. And then every collision is going to be more meaningful, right? Okay. Kind of like if you were driving 50 and you collided, you're going to have a bigger meaning to that reaction, right? Versus if you were driving 5 miles an hour and you collided, you're going to have very little meaning to that reaction, okay? In that case, negative meaning, but in this case, usually positive, okay? You're going to have more reactions happen. Now, when they collide with each other more often, this is going to cause more reactions, but also the amount of particles that's going to be high enough energy to have a meaningful collision is also going to be high. Okay, so that's one of the reasons why we use temperature a lot to speed up reactions, because it has a lot of uses in making that reaction go faster. The other thing we can do is we can increase the amount of reactants. So if we have more reactants, they're going to collide more often. And so we'll get a faster reaction. And that's going to increase the rate of chemical reactions depending on that concentration of reactant. Okay? All right. So again, it's the concentration of the reactant that's going to matter the most here because it's how often they collide, right? Okay. Not just pure amount. All right. Now, as you go on in a reaction, right, what's going to happen to the concentration of reactants? Well, they're going to turn into products, aren't they? And that means you have less and less and less reactants to react. Okay? So this is something that happens over reaction, is it actually tends to go slower and slower and slower as you use up more of the reactants, right? And we all know this already because we've seen fires, right? So what happens to a fire as you burn up all its fuel? It starts going slower and the flame dims, right? And it gets smaller until finally it starts like sputtering and then poof, right? Because it can't maintain itself. And you were actually seeing this effect. Okay, so presence of a catalyst. This is one that most of you or some of you haven't seen before. And the ones who have seen it before, your one you've seen is probably very inconsistent. So I can't like point to a catalyst you've all seen. It's somewhat unusual. You may have seen like a platinum catalyst in hydrogen. Maybe. Like that was on the news quite a bit for a long while, and it was on a lot of like science YouTube and stuff. People like doing that. You may have seen a catalyst and a catalytic converter. Anybody seen that before? No? Okay. 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 That's fair. You've actually maybe seen callus in the form of like acids. You put acid in certain different foods and it causes a reaction to go faster. So you've seen a few callus maybe, but you may have not realized it or known. And so, yeah, most of you will probably be like, this is the callus that I'm actually going to remember. Is this book right here. And me, maybe. So a callus speeds up reaction. It does that by lowering the activation energy. So it makes that big hill smaller so we can go over it faster. Okay? It usually does that by breaking it up into multiple steps. Right? That's the most common type of callus. Is where it takes basically Mount Everest, it breaks it up into a bunch of speed bumps so you can go over it fairly quickly. Okay? All right, so again, the callus participates in a chemical reaction. It's going to, however, remain unchanged and can be used again. Now, that's not to say that callus lasts forever. Okay? Yes, the reaction does not change it, and theoretically, a callus should be able to last forever. In the real world, nothing lasts forever, right? And so if you have a callus, like say a catalytic converter, those oftentimes go bad over time. And so what you'll see is like vehicles that have been on the road for 20, 30 years start emitting black stuff from their tailpipes, right? Do you guys know what percentage of pollution is done by vehicles over 30 years old? It ranges by year, but usually it's up in the 70 to 80%. Okay? Which means it's actually a very small number of vehicles that actually pollute, other than CO2. Okay? CO2 is done by all. But carbon monoxide, nitrogen oxides, which is smog, those things, those are done by a very small portion of the vehicles due to bad catalytic converters usually, but also bad tailpipes and a few other reasons. Okay, so callus is going to be neither a product or reactant. It's a third category. It's a callus. It doesn't get consumed. It doesn't get made. Okay? It gets regenerated as you go along. So it'll never get used up. Acids, bases, metal ions are very common callus. Those are the ones you've probably seen if you've seen them. For example, catalytic converters or metal ions. Acids are very, very common callus. Has anybody ever used superglue? Yeah. That's most superglues are a base callus. So they're base callus. Okay. So you've actually seen a callus use superglue, you just have no idea. So many callus are going to immobilize reactants very close to each other. This is going to increase the likelihood of collisions and therefore the rate of reaction. The most common type of callus is literally one that traps the two near each other in the correct orientation. And so they just keep banging on each other until they react. Okay? That's the most common type of callus that you're probably most familiar with. Enzymes are going to be biological callus. Has anybody heard of enzymes before? Okay, so you have technically heard of callus, may not have known it. But enzymes are callus. Yeah. They're the biological callus. Now, most biochemical reactions are going to use enzymes to increase the reaction rates. For example, without the callus that converts CO2 in your body, that does 1 million times per second. Without that, you would take one breath, and you'd only be able to do that every couple weeks. Okay? Which obviously would not be enough for you to actually survive. Mm-hmm. It is. Yep. Not all callus are enzymes, but all enzymes are callus. They're a subcategory, specifically the biological ones. So most enzymes are proteins. This is actually, so not all enzymes are proteins, but most, the majority, are proteins. Okay. Now, this is how you can envision the use of an enzyme, probably the easiest. And this is called the lock and key model. And what's going to happen is you'll have an active site on the enzyme. It's going to bind what are called substrates. They're the reactants. Okay? They have a special name because they have to bind the enzyme first. right? So it's going to bind your reactants. The fact that they're getting bound first means they're called substrates. Okay. Now, once it binds it, what it's going to do is it's going to force that into a very narrow corridor where they're correctly oriented with respect to each other. And so every collision then becomes much more likely to cause reaction, right? And that's an active site on an enzyme. Everybody good with that so far? Okay. Okay. Now, the truth is that most active sites actually change as they bind these reactants. But I'm not going to go into a huge amount of that. If you're interested in it, there's entire courses that are devoted to that. And it takes a bit more explaining, okay? But it's actually quite a fascinating field. Now, the enzymes are going to be highly specific to the reactants and reactions that they catalyze in the body. The shape, in fact, is going to be very specific to what they do, right? So usually what people say is that the enzyme shape is its function. Kind of like when you look at a tool, right? You look at a screwdriver, well, its shape is its function, isn't it? You look at a wrench, the shape is its function, okay? And the same thing here. Their shapes are going to be their function, okay? Some of them actually look exactly like, have you guys ever seen a machine press? Where it takes like bottles of Coca-Cola, right? And then it takes the metal cap and it, yeah. The ATP production in your body looks exactly like that. It is crazy how similar that looks. It even has like a drive crank. Like you would expect on a factory. Okay? It's just wild how similar those are. But it's because they have very similar things they have to do, right? Take two things, press them together. So, and do it very fast. So when they are defective, when these enzymes are defective, the result is often going to be a disease state in that organism. For example, albinism is the lack of pigment in the skin, hair, and eyes. It's caused by a defect in tyrosinase. It's the enzyme, then the pathway that produces the pigment melanin, and so you can't produce a significant quantities of melanin. Okay. This right here is some different diseases and the enzyme that's actually defective in these diseases. And this would be the clinical symptoms. Everybody okay with that so far? Okay. So let's talk about some different types of reactions. We have these synthesis reactions. These are going to occur when small molecules or atoms combine to create larger molecules. That literally you're synthesizing something, right? Making something bigger, more complex. These products are typically going to have higher free energy because they're going to be less random. Okay, they have less. They have removed entropy from the system. We have put that entropy out to the universe. Okay, and so typically speaking, they're going to have higher energy. The reactants, typically there's more reactants. We're taking two reactants, we're making one product, and so we decrease the randomness. We decrease the entropy. These reactions are only going to have one product when we make them in these synthesis reactions. Now, decomposition reactions, you're going to break apart larger molecules to make smaller molecules. So you can think of decomposition reactions as the opposite to synthesis reactions. So we take a larger molecule, we break it apart into simpler ones. Okay? And so typically speaking, decomposition reactions give energy off. Now, in your body, you actually do this. You do synthesis reactions to make things like glucose, and then you put them into pathways to harvest energy from them. And those pathways are decomposition reactions. Okay? And so you're actually doing this back and forth all the time to store and get energy back out. Exchange reactions, these are sometimes going to be called displacement reactions. This is going to involve both synthesis and decomposition. You can think of, you take one part and you exchange it between the two. Okay? And so you get breaking apart and then recombination, right? Decomposition, synthesis. Okay. Mm-hmm. So when you're looking at that, yeah, when you do like hydrogen and oxygen coming together to form water, that's going to be a synthesis reaction. And then when you react it with something else to form something that's maybe not more complicated, you start with 2, go to 2, that's going to be exchange reactions. Amino acids are the individual building blocks of proteins. And so when you put them together, that's going to be a synthesis reaction, right? Starch, on the other hand, is how you, well, we don't do it, but plants store their energy, and they're going to be broken apart into glucose, and that's a decomposition reaction. We do the breaking apart of starch to glucose. Okay? This right here is actually an exchange reaction. You see that we don't necessarily build something more complex. We start with 2, we get 2 out, and so this one's an exchange reaction. We're exchanging parts of these. Okay, this is a little summary table to this, and that exactly was the double that you were referring to. Yeah. And so you can do a single, in which case you just move one thing, or you can do a double, which in case you swap. Okay, so let's talk a bit about reversible and irreversible reactions. Reversible reactions, these can form products in either direction. They're reversible, you can go back and forth. Okay, so in this case right here, it typically is going to have a double arrow, which apparently the new version of Microsoft does not like my double arrow. So I'm going to have to go back through and replace it again. Every time they update Microsoft, it does that. It just, I don't know. I should probably just start putting it as a picture, huh? Just give up. Now, this is typically a double arrow. So an arrow on top, an arrow on bottom. Okay? And it shows you that it's reversible. You can go back and forth in it. If a chemical bond can be formed with enough input of energy, it can also be broken in this case. Reversible chemical reactions will indicate a pair of arrows. And so in this reaction right here, we can have, if we started with AB, it could go back and form A plus B, right? If we started with A plus B, add it together, we could get AB out. Okay? Now, these oftentimes are going to point to a chemical equilibrium. If you have a reversible reaction, you can form a chemical equilibrium, or go back and forth, and you get an equilibrium point where they don't have a significant exchange between them anymore, where you don't have any buildup of one versus the other. But when we have a chemical equilibrium, what I want to point out here is that you will have both forms. They will continuously be reacting in both directions. Okay? Exactly. Yeah, it has the double arrow. Let me write. Like, okay. They don't have to be equal in size. They can be different in size. This one means that we get more of the product than the reaction. So if we were to have that in equilibrium, it might be 75% product, 25% reaction. Okay? Now, the important part to remember is an equilibrium does not mean that the concentrations, the amount of each, is equal at an equilibrium. Okay? What it means is that the exchange is equal. You don't get an overall change in that state. So everything that reacts to form product, you get reverse reactions equal in speed to make reactant. Now, these equilibriums are typically dynamic equilibriums, and that means they'll have continuous exchange between the two. Now, the reactions that are highly exothermic, these are going to be, for practical purposes, considered irreversible reactions. Because what you're going to see is you just can't get backwards. Okay? It's kind of like if you were to fall off the 3rd floor of this building. Could you jump back up to the 3rd floor of the building? No, we can't, right? It's too high energy, right? If we fell off a step, we could jump back up on the step, right? And so that would be a reversible reaction. You can go back. Okay? Yes. That's the one arrow you're most familiar with. And so that's the single arrow going to a product. And by definition, by convention, you put reactants on the left side, products on the right. Okay. You will notice that reversible reactions, it actually kind of doesn't matter which is which, because you're going both directions, right? So it just depends on what perspective you have, which is reactant to product. Irreversible reactions matters a lot, because you're going from reactants, you're going to products, and it's stuck there. It's not going back. When we break down food, these reactions are never reversed all the way back to reforming the actual food, because there's irreversible reactions that are within that. Okay? And those are actually very key, very important points to maintain our bodily function. That's actually why our bodies can continuously work. Okay? So let's talk a bit more about combustion. This is another type of reaction again. So combustion is going to involve the organic molecules reacting with oxygen to produce carbon dioxide and water. It's a very, very specific reaction that's very important. Okay? So combustion reactions are going to tend to be highly exothermic. They're largely considered irreversible. Anybody ever heard of a fuel cell? Yeah. So fuel cells are actually the process of making these reactions reversible. That's what's special about them. You do the reaction reversibly, and so you can get a much more efficient yield of energy. Typical combustion, though, is highly exothermic and is usually considered irreversible. Now, combustion reactions are going to be a type of decomposition reaction. They're also going to be referred to as oxidation reduction reactions. Oxidation. Yes. Yes. So oxidation reduction reactions, meaning as in you take electrons from one and give the electrons to the other. Okay? In this case, you can kind of guess it's the oxygen that does oxidation, where the name comes from. So, again, we're going to use oxygen. We're going to produce an output energy that's typically going to dissipate as heat. It can also be harvested a little bit to produce work. And so we can perform work using combustion. That's how the combustion engine works, right? Or an energy production facility. The reactions are going to be important for understanding fuels. Most fuels that we know of are going to perform combustion reactions. The products are always going to be carbon dioxide and water. So these are very, very useful for understanding organic chemical reactions, because they're kind of like the introduction you're most familiar with. All right, so let's go ahead and talk a bit about alkanes. Alkanes are going to be the most common combustion reaction fuel. So alkanes are generally can be considered unreactive. They do undergo combustion, but they're not something like if you got next to gasoline, you're not like, oh my goodness, this is just going to spontaneously go up something and do something, right? We have entire fuel stations that are full of gasoline, right? So alkanes are an excellent fuel source because they give off a lot of energy when burned. They're extremely energy dense. So you can transport them, move them around, use them for fuel very easily. The internal combustion engine emits partially reacted hydrocarbons in the exhaustion. This is very common. This is usually fixed by using a catalytic converter to go ahead and complete that combustion. Okay? You can actually, by putting enough oxygen and little enough fuel in, get a complete combustion, but it's very, very tricky, and for a variety of reasons. If you want to look that up, there's a very interesting history to that, where they've been continuously trying to get that better. Hydrocarbons will not be completely oxidized, and that's actually where the carbon soot results. So if you ever see a combustion engine giving off like that black or gray smoke looking stuff, that's soot. Okay? It's uncombusted carbon. You'll notice it looks a lot like the carbon coal, right? Because it's very similar. It's carbon, little tiny carbon fragments. The term clean burning actually refers to the efficiency of the combustion. The cleaner a fuel burns, the more complete the combustion. And so the more of it is just in the forms of CO2 and water. Okay? All right, so let's talk about distinguishing some different chemical reactions. For many of the organic reactions, the interesting part is going to be how the functional groups change as reactants form products. So in an organic chemical reaction, the structure of the organic molecules is going to be written out, showing these connectivities. And we'll see they'll have a difference in that connectivity going to products then. So small molecules that participate in the reaction are going to be shown above the reaction arrow. Reaction conditions will be shown below the reaction arrow. So in this case right here, we have the major reactant, okay, which is butene. This right here is then the hydrogen. That's going to be small molecules that we're reacting with the butene, okay. This is going to give us butane as our product, which is right there. Now, the stuff below the arrow is the platinum catalyst. So in the presence of platinum catalyst, we can cause this reaction to go much faster. Does the catalyst get used up? No. That's why it's a catalyst, right? Okay. Does this hydrogen here get used up? Yes. That's actually one of the reactants. It's just a small molecule. Yes. Yep. We're actually adding it right here. This is actually referred to as an addition reaction, in case you're curious, is the specific name for it. And we add the hydrogen across this double bond, causing the double bond to be broken. That's where these new hydrogens came from. So in the case of this hydrogen going platinum catalyst, you know because it's going to do the addition reaction replacing that double bond. Yeah. Now, if you took more advanced chemistry, like organic chemistry, then it's because of like what a double bond is. Okay. Okay. So let's go ahead and look at something that's more coupled. Okay. In biochemical reactions, you oftentimes have an energy that is actually coupled into it, and that's what drives the reaction forward. For example, you may have oftentimes seen in biology systems these ATP going to ADP arrows like this. Okay? So if you start looking at biochemical reactions, you'd see this a lot. And what's happening here is we have the reactants and the products and the reaction conditions shown right there. And then up here, we have a smaller molecules, or we can have something that is coupled with this. So it's another reaction that's coupled into it. Okay? It's not the main one we're looking at. We don't care about it as much. Right. And so what you'll see here is this ATP right here is actually putting a phosphate group down here. And that's the coupling. We're taking a phosphate from ATP. This right here would be the enzyme that does this reaction. Again, an enzyme's just a catalyst, right? Biological catalyst. Okay. So we'll oftentimes have in biochemistry two reactions that will be written together, and we'll have an energy transfer reaction that's written at this arrow right here. And that's why that's written like that. That's what the ATP is there for. It's literally transferring energy into this. Okay? And then we'll have another reaction over here, and this will be harvesting that energy. So we have a general reaction, we have an organic reaction, and we have the biochemical reactions. Notice the big difference between those is you have a slight rearrangement of how the reaction is written, because in the general reaction, we don't have any like specific thing we're looking at. Okay? In the organic reaction, we're looking at the organic structures. And so all the non-organic structures we don't care about. Okay? And then the biochemical reaction, we're looking at those biochemically important compounds. And so we're stressing those, and we're trying to move the other stuff out of the way so we can, again, selectively focus on the important biochemical molecules. Okay, so this is oxidation reduction. I'm going to, from now on, call this redox. Is everybody okay with that? You see how it's just an abbreviation of those two things? Red, reduction, oxidation. Okay, now when we talk about redox reactions, these are always going to be paired. They're like a yin and yang situation, okay? If you have one, you have to have the other. Or another way of saying that probably makes more sense to you, is that they're like a payer and payee, right? If you have somebody give you $5, somebody had to have lost $5, and you have to gain $5, right? Right, okay with that concept? Okay. So if you have an oxidation, then you always have a reduction, okay? If you have a reduction, you always had to have had an oxidation as well. Okay? A take and give. Now, they're often going to be involving metal ions and the movement of electrons. That would be the inorganic. They can also involve the addition or removal of oxygen and hydrogens. This would typically be a more biochemical, organic style. Okay? And so right here, we actually see a reducing agent. So first off, let me start with the oxidation. Okay? Oxidation is where you lose an electron. So we have this right here. It loses its electron, and it is oxidized. We had an oxidation occur. So remember, oxidation is the loss of an electron. Reduction is going to be gaining electrons. The electrons are negative, so when you gain an electron, you are reduced. Okay? Everybody got that terminology so far? Okay. If you gain a debt, you're reduced, aren't you? If you gain a negative, you're reduced. Okay? Gaining an electron is gaining a negative, you're going to be reduced. The opposite of that is losing the electron, which is oxidation. Okay, so the second set of terminology we have to discuss is going to be the agent terminology. So the reducing agent is going to reduce something. So this is our reducing agent because it causes the other thing to be reduced. This one right here is our oxidizing agent because we cause the other thing to get oxidized, right? Okay. Kind of like the assassinating agent is the one that killed someone, right? Not the one that died. Okay. Okay. Or the lone agent is the one that caused you to gain more debts. Though sometimes that's possible. To make that more complicated. Is everybody okay with that terminology so far? Make sure you practice. So the inorganic oxidation reductions, you're all very familiar with one of these, and that is rusting. Okay? We have iron metal, and this could be in steel or iron. They both have iron metal in them. And what's going to happen is we'll have the iron metal, which does not have a charge. Oxygen in the atmosphere is going to take electrons from that iron metal, making it into the form of iron 3+, mostly. This is going to give us rust, which is this iron oxide here. Is that making sense? Okay. Can everybody see that okay? Okay. So iron lost electrons. So iron was oxidized, right? Oxygen gained electrons. Oxygen was reduced, right? One of the most common oxidizing agents is oxygen. That's actually where the terminology comes from. So like oxygen oxidizes things. Mm-hmm. Yep. You got it. You got it. Remember that trend with like electronegativity and an F is 4.0? That is actually a measure of how well this does that. Yeah. If it does it well enough, we get this full-on loss of electron, and that is redox reactions. Yeah. Negatives get reduced, and they're gaining electrons. Okay? Positives get oxidized, they're losing electrons. Exactly correct. Okay. And so remember the terminology. There is a acronym for it. In my experience, it doesn't actually help almost anyone. But I'm going to tell you it just so in case you're one of the very few people that will actually help. Okay? You can try it and see if it helps. It's oil rig. And so oxidation is loss, reduction is gain. Okay? I've had far more success with electrons are negative, so you are reduced. Okay? Gain a negative, you're reduced. But maybe you're going to be one of the people this will help, in which case I'm glad I got an extra person. Okay. Whichever way, there's also songs, if you're good at remembering songs, that you can look up, set to every beat you can imagine. Now, let's talk about oxidation reduction in biological systems. So metals are also oxidized and reduced in biological systems. This is actually cytochrome C. It plays an important role in ATP reduction, actually. And we can see here it's actually losing an electron. Everybody see okay? So that iron is losing an electron and becoming more positive. And so that is being oxidized. Then whenever we reset, we would actually go back and it would be reduced. Okay? And so it goes back and forth. That iron is actually held in place by a small organic molecule. This is that organic molecule here. It looks a bit like a crown. Has anybody seen their crowns, little spikes coming up? Okay. So it looks like a crown if you look at it three-dimensionally. And then you have this little iron that sets on top of it, like so. Okay. And this is the heme group. You may notice that you may have heard of hemoglobin. That's the same heme. Okay. Hemoglobin refers to the heme group like this. Okay. So let's talk about oxidation reduction and more organic biochemistry style. Okay. So organic molecules typically are going to be oxidized because it gains an oxygen or it loses a hydrogen. Okay, oftentimes both. But so if you gain an oxygen or lose a hydrogen, that molecule got oxidized. So right here we actually see an example of this. This right here is a carbonyl. We oxidize it. We go to a carboxylic acid. So yeah, gained an oxygen. Okay, if we reduce it, we're going to go to an alcohol. And this right here is reduction. We added a hydrogen, right? Okay, so right now we're concentrating on seeing that we added a hydrogen and going, that's a reduction. Okay? And seeing that an oxygen was added instead, we lost hydrogens, and so that one right there is an oxidation, right? I need you to understand those things first. We won't really go that far into like why these reactions occur and how they occur and what you can predict the reactant product. We just don't have time for that. That class is actually organic chemistry. Yeah. But we'll go like a very fine skimming of this. Okay? And we'll go just a little bit detail. All right. Now, this, by the way, is how your liver would oxidize alcohol, in case you're curious. And this is actually why it causes damage, is because when it oxidizes alcohol, you get a ketone right here, or an aldehyde in this case. And then you get right here a carboxylic acid, and that causes very minute damages to your liver. This is why if anybody ever drinks rubbing alcohol, they get much worse damage and can die from it. Is because this right here is called formic acid. And it's what like ants and the Asian beetles use to bite you with. That's actually how they bite you. They spray you with formic acid. It tans your flesh like leather. Okay. So oxidation in cells, when we fuel our bodies with nutrients that are broken down through oxidation. So in the body, the process of combustion is going to occur through a chemical pathway. It's going to be a number of reactions all added together. The series of reactions through glucose is combusted into a type of cellular respiration. So what you'll see in the body is that instead of having a single combustion reaction, it's split into a bunch of steps, and then they undergo what's called cellular respiration. Okay, it's overall the same sort of reaction. It's just broken up into a whole lot of steps so you don't burn yourself to death. Okay. Now, ethanol is actually oxidized to aldehyde ethanal, and that's the ethanol right there is the aldehyde version of that, like I was discussing before. This is also called acetaldehyde, and this is done by liver alcohol dehydrogenase. In the case of ethanol oxidation, the molecule that undergoing reduction is actually NAD+. You may have seen this somewhere. NAD+ versus NADH. And so whenever you have a reduction reaction and a redox reaction in your body, this is going to be formed with NADH and NAD+ typically. Okay? There is one other molecule that sometimes is used, and that is FAD. And so these are going to be two of your most important redox molecules in your body. Usually when you have a redox reaction, you're going to see one of these two involved somewhere. This right here is going to be an oxidation of the alcohol. This one right here is the alcohol that people drink, ethanol. And this right here is ethanal. And you can see here, this is being oxidized. See how we have less hydrogens on this carbon here? So that one's oxidized. This right here is being reduced. See how we have more hydrogens on it? Yeah. And this is the enzyme, by the way. That's the abbreviation. Okay, so this is going to be a condensation reaction. Now, condensation reactions is when you're going to produce water as two organic molecules are joined. Condensation reactions can occur among functional groups that have a hydrogen and an OH that are in a polar bond. Then we can remove those as water as the reaction goes on. In a hydrolysis reaction, we're going to do the exact reverse. And so instead of removing the water as the reaction goes on, we're actually joining the two. We're going to use water to split the two up. So we're going to add water across and split the two up. Okay? Hydro means water, obviously, and lysis means to break. And so hydrolysis reaction using water to break. Okay? Now, this is going to split that up into two smaller molecules. And so here we see a condensation reaction going forwards. And we can see they're joined together with water involved. This is going to be a hydrolysis reaction. And you can see we're splitting it up. And we added water between them. Everybody see okay? They're just other stuff. For example, this is the reaction that shows up in like a synthesizing a protein from amino acids. Okay.
Science?
What's that?
That's all I recall.
Is it all? That's fair. That's fair.
They did. What's that? That was the only stuff.
Okay, so cool thing, the mitochondria was actually its own organism at one point. It's a symbiotic organism that has lost the ability to breed and exist without its own. Okay, so kind of cool thing. It has its own DNA. That DNA is only passed from the mother. And mitochondria is actually, yeah, it does produce the ATP. That's not the only source of power in your cells, but it is the most efficient part of your power generation and harvesting. And it also produces most of the small molecules you need to make everything else. So it's very, very important for you to continue living, which is pretty trippy if you start thinking about it. We become so dependent on the ATP and the mitochondria. Now, the condensation and hydrolysis reactions, very common in biochemistry. You'll notice right here that ATP we had been discussing was a hydrolysis reaction when you were joining these together. Can everybody see that? When you're splitting them apart, excuse me. And when you're joining them together, that was a condensation reaction. So when you harvest the energy for ATP, it is oftentimes going to be a hydrolysis reaction of some sort that does that finishing harvesting. Okay. When you're making it, it is a condensation reaction. Mm-hmm.
So it's like pretty much the exact same.
Mm-hmm. Yep. Yep. See that we have the water here, and then we have the OH here, and this right here, this is acid base, and so physiologically, it's going to be an acid. It'll donate its H plus and have the negative charge. Typically, it's not going to specify like physiologically or acid base because you're not even in that part of the chapters. So typically, you'd have to put the hydrogen just right here.
They give us crazy fun.
Yep, you have to. What they're trying to have you do is, well, it's very useful for you to learn the reactions and learn the structures by actually drawing them out. You learn far better. Mm-hmm. Okay. Come on into office hours, and we can try drawing a few out. Okay. All right. So, carboxylation. Now, this is going to be where reactions are going to involve the addition of a carboxyl or carboxylic acid group. And so this is going to be like this. See, we have a carboxylic acid group right here. And this is carboxylation. We've added a carboxylic acid group to it. Right there. Now, notice that carbon dioxide moving through your cells. In this case, we're going to add that to the oxaloacetate here. And this is typically done by an enzyme that's called a type of enzyme that's called carboxylase and decarboxylase. These do these reactions for most of these. There are different forms of them depending on which one it reacts. Okay. So this right here is going to be where we have a phosphorylation or dephosphorylation. You can probably guess which each one does from the names. And what's going to happen is we're going to add a phosphate group here for phosphorylation. Dephosphorylation is going to remove that phosphate group. Okay. It's extremely important for things like modulating enzymes and making them work or stop working. Okay. And so this right here is 1-phosphate, PI. That would be this right here. That's how you note it as a single letter. PI, inorganic phosphate. Very common for regulating chemical pathways, making them work faster or slower, or trying to disable them as much as possible. Okay. Note that they're a condensation and hydrolysis reaction when you look at these. They're just a very specific form of it. And so we have enzymes that catalyze condensation reactions involving phosphates. These are going to be phosphorylases. We have the enzymes that catalyze the hydrolysis. That's going to be phosphatases. So condensation, phosphorylases, hydrolysis, phosphatases. Okay, so these are going to be hydrolyzable and non-hydrolyzable lipids. So hydrolyzable lipids, these are going to react in a hydrolysis reaction. They're going to form simpler compounds. And so we will break these apart to form these simpler compounds. You will notice that it's going to involve water and hydrolysis, right? So we're breaking that apart to form the simpler compound right there. Non-hydrolyzable lipids cannot undergo hydrolysis. So they are not going to be able to do the hydrolysis reaction. Some of the different hydrolyzable lipids are going to be fats, oils, waxes, and the important group for these is that they contain this right here, which is called ester group. And that's what allows them to be hydrolyzable. Okay. An interesting side note to this is actually how you form things like soap, in case you're wondering. So if you take an oil, you can put it with sodium hydroxide, And you can do a hydrolyzable lipid, that's the oil. You can then form this right here, which is carboxylic acid. And under basic conditions, carboxylic acids will form soaps. That's how you actually make soap. This is a typical example of a fat or oil that can be hydrolyzable. This one has glycerol here, which is this head part, and then 3 fatty acid chains, which then split off when we do the hydrolysis reaction. Okay, so in addition to an alkene, an atom or group of atoms is going to be added to that double bond. This is the addition reaction we've been talking about before. Remember the hydrogen adding across that double bond. So this is going to be the addition reaction, where we add something across the double bond and it will break the double bond. Okay? It can be a variety of different things. It could be HCl, it could be H2, but that's the overall reaction. So this is probably the single easiest one to always find and tell what type of reaction this is, because you always break the double bond and then add the things across it. Okay, so let's talk about that hydrogenation. Hydrogenation is one of the addition reactions. And so the hydrogenation in trans fats, you may have heard of this before, because it's a health concern that people have had. And in a hydrogenation reaction, you're going to have 2 hydrogen atoms that are going to be added across a double bond to form a single bond. And so you'll add them across an alkene double bond. It'll give you an alkane. You do this in the presence of a catalyst to make it go faster. The catalyst is typically platinum, nickel, or palladium. Now, this reaction is very difficult to control. So what ends up happening is you don't always get all alkanes. This is actually an equilibrium. It's a reversible reaction. So you can get some of the double bonds coming back. And so instead of just having all alkanes, you typically generate a little bit of the ones with double bonds. When those double bonds come back, though, they don't have to come back as the cis double bonds that we've seen in all these fatty acids that have the double bonds. So see this one up here? These right here? Those were those cis double bonds, right? Okay. So if you hydrogenate these, most of that is going to end up as an alkane. Single bonds only, like so. You'll just get the alkane, single bond. And that'll be the saturated fatty acid, right? But some of these are going to come back, some as the cis double bond, but some as the trans double bond. Okay? And that trans double bond had these carbons on the opposite side, if you remember from cis versus trans that we talked about before. And so that's actually what ends up happening where it creates trans fats. And this reaction is called partial hydrogenation. And so what you'll see here is that, let's say we had taken this fatty acid we looked at before, we hydrogenated it, and we got partial hydrogenation. What's going to end up happening is, most of these chains are going to end up the saturated fatty acid right here. Okay? And so those are the saturated ones, all with single bonds. But every now and then, one of these double bonds is going to come back, and it's going to come back as a trans fatty acid. Okay? This has health consequences to people. The trans fatty acids do not fit in your cell membranes the same way as a saturated or cis fatty acid. Okay? They don't get used the same by your body. Okay, let's talk about hydration. Hydration is going to be where you have hyd, as in hydro, right, water, and we're going to add water across the double bond. This is typically done in the presence of an acid, and so acid in this case is actually a catalyst. And so we'll add water across the double bond, and that's going to give us an alcohol here. Okay? Notice that's just an addition reaction where we've added water across the double bond. Okay, now, whenever we do hydration, this is going to be asymmetric. You have one that's a hydrogen and one that's an OH that's getting added across this. So if it's an asymmetric double bond, this is actually going to follow a Russian chemist's rule This is called the Markovnikov rule. And what's going to happen is the OH is going to be added always to the side with more carbon groups attached. So if we look here, we do a hydration, that OH is going to end up on this side because it has more carbons attached. The hydrogens always go to the side with the more hydrogens. Okay, and that's Markovnikov's rule. All right. That is the end of the chapter. I'm just going to take questions for the rest of the time. If you want to try to do that question, we can. And I'm going to call that a day. We'll start up on 1 on 6 next time. Okay? All right. Okay. What I might do is I might bring it up here and see if we... I'm assuming chapter 5.
Everything like eligible to
Okay. Coming to me, officers or tutoring, or both, some combination thereof. And I can help try to work